So the only topic we have left now is some small topics. First is current divider, and then we have voltage divider. These are just names. The only thing about this is that when there is a current I passing here, let's say there is I current flowing, and I take two resistors. Let's say this is a resistor R1 and this is resistor R2. So the current flowing gets divided into two parts, I1 and I2. So I want to know the current flowing through them. What would be the magnitude of the current which is flowing through them? So let's say the I current is flowing like this, and I put two resistors in the circuit, in between the circuit in the path, and they are added parallelly. So there would be current divided in these two resistors. And what would be the value of I1 and I2 in this case? So the formula of current is simply given by I1 is equal to I, which is the current going inside, into R2 over R1 plus R2. What it means is that the lower is the current, the lower is the resistance, the higher is the current. So the current gets divided in the ratio dependent on the R1 and R2. So let's say the sum of R1 and R2 is this, and then the ratio in which the current will go to, the ratio in which current divides is like this: R1 over R1 plus R2 and R2 over R1 plus R2. This is how the current gets divided into parts. In these parts the current gets divided, but the larger part would be in the smaller resistance. So if R2 resistance is large, then this current should be passing through this R1 resistance. So if I want to find the current I1, so I will take R2 here. If I want to find the current I2, so I will take R1 here, this part of the I current. And this can also be written as I1 is equal to R equivalent into I divided by R1. Means the larger is the resistance, the lesser is the current. And I2 will become I into R equivalent divided by R1, where R equivalent is simply R1 into R2 divided by R1 plus R2. This is R equivalent. Similarly, in case of voltage divider, let's say there is a potential across 2 points is, let's say this is A and this is potential V8 here. These two are having two resistors in between them. This is R1 and this is R2. Since if I add the resistors parallelly and provide them potential from these sides A and B, the potential difference for both of them will be same. So in this case there is no voltage divider. In this case there is no voltage divider, and in this case there is no current divider case, because all the current passing through here, this would be equal to the all the current passing through all the current passing I would pass through this R1 resistor and R2 resistance also. So it is easy to tell the current passing through them. And in this case, if I provide a V potential difference across these two resistors, it is easy to tell that this potential difference would be across this R1 resistance and also across this R2 resistance. So these type of cases we don't need, only we have to take the current divider case in case of parallel combination and voltage divider in case of series combination. So here in this case we know that the potential difference across A to B is, let's say, V. So the voltage across this R1 resistance, let's say it is V1, and let's say it is V2 across this resistor. Across this resistor the potential difference is V2, and across this resistor the potential difference is V1. So V1 would be equal to V times R1 upon R1 plus R2. Same logic as here, the current will get divided in the ratio of these values, and we know that the higher is the resistance, the higher potential difference it needs to provide the same amount of current. So to provide the same amount of current, the higher resistance needs higher potential. So we will simply say that for the larger is the resistance, the larger is the current through potential difference. Similarly, Vt is equal to V into R2 over R1 plus R2. Now this can be this is it is this. Okay, so now talking about galvanometer. So just remember this and this for divider cases. Now moving ahead, galvanometer. How does a galvanometer function? So galvanometer is just simply a device in which there is a magnet. There are two magnets with, let's say, north pole here, south pole here, which create some fields, and there is a coil in this. It like a motor. It is little bit like a motor, and this is a coil. It has two ends. This wire has two ends, and this coil is wound around a core of iron. There is an iron core around which the coil is wound, and what happens is that when the current is provided to this wire of, let's say, resistance R naught, and when the current is provided it creates some magnetic field, and this magnetic field interacts with the magnetic field of these permanent magnets, and this coil gets tilted by some angle, and a spring is added also, a spring of some a spring which works like the torque on the spring applied is directly proportional to the amount of the torque applied on this coil is directly proportional to the current passing through this coil, and the torque that the spring stores, the tower storing of the spring is directly proportional to the theta angle this device rotates. So somehow we can create a device on which there is relation between current and angle theta. Let's say if I put a needle here, then the angle of theta tilts is directly related to the current flowing through this coil. So what happens is that there is such a device as a galvanometer, and the galvanometer has some resistance, let's say R naught, or let's say Rg is the resistance of galvanometer, and there is a and to make this is just simply a galvanometer. And now if I want to make an ammeter, this galvanometer resistance is little bit large. So in case of ammeter which is added in the circuit just in between, like let's say this is a circuit, and there is a bulb here, resistor here, and I connect it to the cell. So the ammeter is connected in the series of the circuit, so it can tell the actual amount of current passing through it. So to make sure that this ammeter does not change the value of current passing through this circuit, we make sure that we connect a very small resistance along parallel to this resistor, which is shunt resistor, so that when I connect this shunt resistor here, which is very small resistance, so it does not affect the current in this circuit, and parallel to it I will add the Rg, this galvanometer. So this whole setup is ammeter. This galvanometer is fixed. It is made, this whole ammeter is made in such a way that it calculates the current passing, it measures the current passing through this resistor of galvanometer, and converts it into, let's say the current flowing through this is I, and the current flowing through this shunt is Is, and the current that will flow through this galvanometer is Ig. This is a current divider case. So in this case we know that the total current passing through this circuit is equal to some K times Ig. There would be some constant value to which with which I multiply Ig. If multiplied by Ig, then it gives the total current through this circuit. Using this factor in the galvanometer, we can make the current and theta relation like in such a manner that the current deflections, the current which causes deflections, Ig, it shows the reading of I1. So that's it. The current passing through this galvanometer is Ig, but it shows the value of the current passing through this circuit I. So it tells the sum of the current passing through both. And since we know the voltage divider, current divider, I can say that Ig is equal to I times R shunt divided by R shunt divided by R shunt plus Rg. So this is a constant value. So this is how we can relate the Ig and I. And the value of Rs is needed to be very small, tending to 0, so that it does not affect the circuit's current. Okay, so for ideal ammeter, this Rs, it should be approximately 0. This Rs should tend to be 0. That's it. But if this Rs becomes 0, there would be no current passing through this galvanometer resistor. So that's why there is no ideal ammeter possible. Now Next thing is potenti potentiometer, sorry, voltmeter. Voltmeter. So what is a voltmeter? A voltmeter has similar settings. There is a circuit here and there is some resistor. Across this resistor there would be some potential difference, there would be some current I passing through it. And if I want to find the potential difference across it, let's say A and B point, then the voltmeter is connected parallel to it, so that what happens, it can measure the potential at these two ends. And due to the potential at these two ends, there would be some current flowing through this, which is I. And it is needed to make sure that it the resistance of this voltmeter does not affect the resistance between A and B. We know that if it is parallelly added, then the total resistance of this combination is 1 upon R is equal to RAB is equal to 1 upon resistance of the resistance in the circuit, which is 1 upon R, plus resistance of voltmeter 1 upon RV. So to make sure that the total resistance RAB remains 1 upon this R, so we will need to make sure that this resistance value tends to be infinity, so that this value becomes 0 and 1 upon RAB becomes R. So in voltmeter, we use a galvanometer, which is RG resistance, and parallel to it, or not parallel to it, in series to it, there is a very large resistance which tend to be infinity. Let's say R not resistance which tends to be infinity, which tends to the infinity, so that the resistance of this whole circuit is very large. And this is voltmeter, and this is added in parallel to the resistor to calculate the potential across it, potential difference across it. And this RG resistor has some coil which has some a needle and a reading scale which tells the potential values. And we know that current flowing through this galvanometer, which is Ig, that is that has some relation to the potential across this whole circuit. How it is related, we can say that the total resistance across AB is, let's say, R, and the total potential difference is V. And since current, let's say Ig current is flowing, then that would be equal to Rg plus R naught. So this is the resistance of the device, this is the resistance of the device, voltmeter, and this is the current passing through the galvanometer. So somehow this current in the galvanometer is related to the potential in the across this wire. So we can tell the voltage, because this is related to the angle theta, so this will become related to the angle theta of deflection also. So voltage can be told by the deflections. So this is the working mechanism of voltmeter and ammeter. Ammeter always tells the total current passing through both, sum of the current passing through both, or we can say that total current passing through this ammeter. That is was it is what the ammeter shows in the reading. And in case of voltmeter, it tells the potential difference across A and B. And if current gets changed, if we know that the potential difference across A and B is equal to the current passing through them across this wire I and the resistance R. If the current gets changed in the circuit, then since I get changed, the potential across AB will also get changed. So we need to make sure that there is no effect of this voltmeter on the resistance of the circuit. Next topic is meter bridge. meter bridge. It works on the principle of the Wheatstone bridge. In Wheatstone bridge, the we had registers here R1, R2, R3, R4, and this was R5. Now it was said that generally this side is called P, Q, and this is R, and this is S. P, Q, R, S. I guess this is the order we generally take in. अभी बीच वाला पार्ट काट देना अभी थोड़ी देर का. कुछ कन्वेंशन लेते हैं हम व्हीटस्टोन ब्रिज में. दिया नहीं गैस व्हीटस्टोन ब्रिज. था तो हो गया. हाँ पी के हमारे सही है. Okay, start. So in general, the let's say this is a Wheatstone bridge we have made, and a current is provided, and some a battery is connected across these two ends. Now what happens is that in general these sides are taken as P, Q, R, S in this order, and let's say this R1 by R4 is equal to R2 by R3. Then in that case we see that it implies that current in the fifth register R5 register, I in the R5 register would be equal to 0. So if the ratio of these two is equal to the ratio of these two, then there would be no current flowing in this. So we can simply remove this resistor. There would be no effect of it, and this can also be written as R1 over R2 is equal to R4 upon R3. And if I, instead of these 2 points, if I connect them like this, and if this condition was followed before, then I would say this R1 by R2 is equal to R4 by R3 is also followed. It means that if I connect a resistor here now, R5, and provide the same potential like I did before, but in this manner, then still the current in this would be 0. Then the current in this would be 0 again. Means if I connect like this or like this, if it is a Wheatstone bridge, it will give the same conditions in both cases. And meter bridge, in this meter bridge we have similar arrangement. Here one resistor which is called resistance box. There is a resistance box here, and there is a resistance box. Its resistance can be varied, and it is connected to a resistor, which, let's say the resistor is, this is an unknown resistor. Let's say the resistance value is R. or okay, this is unknown value of resistance R. This is unknown. Let's say there is an unknown value of resistance R, and this is connected to the resistance box. Let's say its resistance is, let's denote it by the resistance R naught. And now parallel to this, we have a wire. This whole thing is connected to a wire from length A to B. In general, this length, let's say this length is L, and in general this length is taken as 1 meter. It is not always necessary to take this as 1 meter. In general, in meter bridge, because its name is a meter bridge, it is taken as 1 meter in length. But the concept is that if it is a uniform cross section wire, it is a uniform wire of uniform resistivity, uniform area of cross section, and let's say the length is L, this length is L, and from this point I take a galvanometer here and and a, and a key here. What is this called? Jockey. This is called jockey. So there is a pen-like object connected to this galvanometer, which is called jockey, which we move over this wire. This wire is not insulated, means, and this is a conducting part. This connects these two. This connects the, this makes connection with this wire at any point where we touch it. And now what happens is that we provide a current across one end here, and according to this whole setup, we will provide a current, a, we will join the battery here. This is a switch, and the another end would be at here. And let's say this is joined at this point. Let's say this is, let's say this point of junction is J. Then this will look similar to this Wheatstone bridge, and when, and the resistance of this length would be, let's say, R1, and this would be R2. So the ratio of the resistance of these two parts is simply R1 is directly proportional to L. R1 is directly proportional to L1, which is the length from A to this J, which is L1, and length from B to this J is L2, let's say. So, and L1 is equal, L1 plus L2 is equal to L. So we know that R1 is directly proportional to L1 and R2 is directly proportional to L2. And in equality, we will put the same constant in both cases. The only difference is due to the length. So the resist, if it, if the current in this galvanometer becomes zero, which happens when the condition of Wheatstone bridge is found, which means if R0 over R1 is equal to R over R2, when the galvanometer reading becomes zero, we will move this jockey on this wire, so that the, so that until when we get the zero reading of current in this galvanometer. And when we get zero reading of in the galvanometer, it means that this condition is produced. And since this is the condition produced here, we can say that since R1, this can be taken here, R1 by R2, R1 by R2 is, can be written as, this will become R0 is equal to R into R1 by R2 is simply L1 over L2, or I can write it as R is equal to, the unknown resistance R is equal to R0 times L2 over L1, which can be written as R0 times L2 over 100 minus L2 or sorry L minus L2, the total length L minus L2, or we can also write it as R naught times L1, sorry L1 below and L minus L1. So we can write this R resistance in this case. This is how we will calculate the unknown resistor in case of this. And in general, the length is given from this A point, and whatever, it depends on the arrangement of the resistors in the circuit. So next topic is potentiometer, and this is what potentiometer looks like. In case of potentiometer, we can use potentiometer for two things. One is to find the internal resistance of any cell, and the other is to find the potential of any cell, the ratio of potential of any cells. So first thing is, let's say there is a battery here which is connected to a point A here, and this is point B, and this is a resistor, which has some row resistivity area of cross section A, and its length is, let's say, L. Now there is a variable resistance here also, which is rho state. This is the sign of a, how do we write rho state? Rho state, RHEO STAT. So there is a rho state here whose resistance can be varied, so to control the current flowing in this, and the EMF, so we can control the EMF across this VAB also. Now the thing we do is, here we take the one end and connect to it to the cell. Let's say this is the cell, and its cell's positive end is connected to this side which has the positives, and let's say the cell in this device, its positive end is here, so we will connect the positive end of the another cell of EMF E1, let's say, to the same side, and there would be another cell E2 of E2 EMF. It would be connected again to the same side, its positive side would be connected to the same side. Now what happens is that we take this end and take a galvanometer, and then we take a galvanometer, and there is a jockey here, and we move it on this line, and let's say at any J point we placed this jockey at any J point on this wire of length L, and this is a galvanometer. What happens is that the circuit starts looking like this. Due to this circuit, there would be some current flowing in this direction, and since this A to B point, this is going from A to B, this is a cell of EMF1, and let's say it is connected to this J point, and due to this larger cell here in this circuit, there is some current flowing in this direction, and let's say this part has resistance R. Let's say this part between A to this J has resistance R. Then since the current is flowing in this direction, this R into I, and there is a galvanometer here, and the potential difference across this AB would be the potential difference across this, and when the current becomes zero in this galvanometer, when the current becomes zero, means here there is some I current flowing, and when this becomes zero, means the needle deflection starts showing zero in this galvanometer. Then in this case, since we know that the potential difference across the cell, which is VA, from across the cell, which is VA and VA minus VG, this would be equal to the EMF of the cell when there is no current flowing through this cell. Since there is no current flowing through the cell, the potential difference across this resistor would be equal to this Ri. And let's say the resistance of this, since resistivity is given, area is given, so we can say the resistance of this wire is simply rho L by A, where L is the length. Sorry, let's say this whole length is capital N and this small length is L. So for this E1 EMF case, let's say the length found of this A to J is L1. So R1 will become rho L1 upon A1. So the potential E1 can be written as I1 R1, which is equal to which gives that I1 is directly proportional to L1, which means E1 is directly proportional to L1. And let's say I remove this cell and now place another cell of E2 EMF. Now again same thing we will do. We will move this jockey along this line and we will find another I is equal to 0 case. And in that case, let's say the needle becomes 0 when the length between A to J is L2. So we will get E2, let's say this E1 is equal to K times some K times L1, then this E2 will become some K times L2. And the current in the circuit in both of the cases is I. In both the cases the current flowing in the circuit was I. So we can simply say that E1 over E2 is equal to KL1 upon KL2. So we can say that E1 upon E2, the ratio of these two cells EMFs is equal to L1 upon L2 observed in the potentiometer. So this setup is used to compare the EMFs of two cells, and this is the best way of comparing potentials, because this will tell the accurate potential, because there is no current flowing through the cell. So since there is no current flowing through the cell, there would be the potential across the cell would be exactly equal to the EMF, because we can only measure the potential across this cell, and then this potential becomes EMF of the cell only when the current through the cell becomes 0. When the current through the cell when this I becomes 0, only then this will be possible. So that is why potentiometer is a good method of measuring potentials. Now next thing is measuring the internal resistance of a cell. In this case we will take only one cell. This setup is same as before. This is A end, this is B end, and now what we do is that we take a cell here. Its positive end is connected to this positive end side, and it has, let's say, EMF E, and parallel to it we take a resistance box here. This is a resistance box here which is taken parallel to it, and there is a key used, and this is connected like this. Or we can simply say that, or like this. Now there is a galvanometer here and there is a jockey here. Now what happens in this case is that first we turn off this switch, which means we find the length L on we make the jockey, we touch this jockey on this line AB and find the case when the current through this cell would become zero, and it happens when the, let's say, since the switch is open, we will call this L length in this case as L open. L open means when the resistance, when this key is open here. So in that case, when this choke is connected here, this length is, let's say, L rho A, rho L by A. This is the resistance of this part, and let's say there is I current flowing through it. Then I into this value would be equal to the EMF of the cell when this current becomes zero. And now next thing is, and this L we can call it, this part can, we can call it, this whole part can, we can call as constant K, and into L open. This L can be called as L open because the switch is open in this case, and this is equal to EMF of the cell. Now what we do is that we connect, now we will switch on, we switch on this key, and we close this key, and this resistance box is now also a part of the circuit, and some current flows from this part also. Now in this case, when we put this, when we touch this here, jockey here, it shifts position and the length changes to different length L. Let's say, let's call it L close because the switch is closed now. So in this case, we get the, there is some potential V across it in this case, and this V across it is equal to the K times L close. That's it. The potential difference across the cell. This was also the potential difference, but since the current through this cell was zero in a previous case, because this was not part of the circuit in previous case, and the current was zero, so the current through the cell was zero, and this means the what potential difference we measured was actually equal to the EMF. But in this case where the switch is closed, there would be some current flowing in this loop, so there would be some current flowing in this across this cell, and therefore this potential difference will not be the EMF, and this V would be equal to V is equal to E minus IR. So I can write this L close as E minus IR, where this I is the current flowing across this resistor, and in this loop we can say that here, so the ratio of these two is L open upon L close is equal to E upon E minus IR. That is the ratio of these two. And one more thing here is that this, we know that V is equal to IR, and E is equal to IR plus IR. So this ratio, which was the ratio of E upon V, this was the ratio of E upon V, which can be written as, this can be also written as, this is E, which is R plus R upon R. So this L open upon L close can be written as R plus R upon R. Now when we simplify this, we will get the equation which is R is equal to the resistance of this resistance box, which is R. The resistance we have taken for this resistance box, let's say R, then multiplied by the L open and L close minus 1. this is the internal resistance of this cell. This tells the internal resistance of this cell. So this is the formula: resistance of this resistance box and multiplied by the bracket length of this length up to this end between this A and J when the key is open, divided by the length when the key is closed, minus 1. So chapter is over.